So we'll take a quick look through the Unit 9 review sheet. So this is in addition to the two sheets we've been doing in class. So first thing, simplifying some of these rational, these exponent problems. So with number 1, or number 5, I guess, as it's listed here, we have the 4, and then end up with 5 v's and 4 u's. Nothing needs to move because we don't have any negative exponents. Number 6, we don't have any negative exponents either. So 4 times 2 is 8, times 3 is 24, and then there's an x, there's 3 more x's and 2 more x's, so that's 4, that's a total of 6 x's, so we have x to the 6th. And then with the y's, there's y to the 0, which doesn't do much for us, and then we have y to the 4th, and then 1y there, so you have a total of 5 y's. Here, remember, you kind of distribute that third power to everything inside the parentheses. So 2 to the third, a to the ninth, and then 0 times 3 is still 0. 2 to the third is 8, a to the ninth, and then remember, anything to the 0 power equals 1, so really it's like it's not even there. Here, you distribute that 0 to everything. You end up with 4 to the 0, 0 times 4 is 0, negative 1 times 0 is 0, and all these are just going to be 1. 1 times 1 times 1 times 1 equals 1. Right here, this x to the 0, really don't even need that there, so I'm going to rewrite this thing without it, over 3y. So we have x to the third y squared over 3y, and now these y's can kind of cancel out, and what we'd be left with, the x to the third, nothing's going to affect it. The 3, nothing's going to affect it. But what we end up with is 1 extra y left in the numerator there. All right, so we have some negative exponents here. So a squared stays put in the numerator and denominator. But that b squared is going to go to the top. This b to the 4th is going to go to the bottom. And now simplify what we can simplify. The a squareds are going to cancel out. The b squared on the top is going to cancel out, leaving me with 1 in the top and then 2 b's in the bottom. Because there's extra b's in the bottom, we still have to leave b down in the denominator right there. All right, number 11, a lot going on here. That 2 is outside the total parentheses, so everything in here gets that squared. So we end up with 2 squared, y squared, x to the 8th over x to the negative 8th, y to the negative 4th, x to the 4th, y to the 4th. All right, so 2 squared is 4. The y squared is going to stay put. The x to the 8th is going to stay put. Here we have x to the negative 8th, so let's pull that x to the top. We have y to the negative 4th, so let's pull that to the top. And then the x to the 4th, y to the 4th stays put. All right, now let's combine what we can. So we have 4, and there's 16 x's in the top. There's 6 y's, x to the 4th, y to the 4th. Now, one step away here. Let's simplify. So the 4 is going to stay put. Looks like there's 16 x's in the top, 4 y's, which would mean that there are 12 x's left in the top, and then 6 y's in the numerator, 4 in the denominator, which would leave with y squared, and there's nothing left in the denominator, so we can just leave our answer right there. And then finally, number 12, this third just goes to those two pieces, so leave a to the 4th, b to the 4th alone, and then we end up with a to the 6th, b to the 6th. So by the time all is said and done, we end up with 10 a's and 10 b's. All right, the next page, solving those equations. Remember, when we get like bases. So here we have 2 to the 3n. We need to think, how do we get 16 to base 2? And I believe if we do a little bit of work, that's the same thing as 2 to the 4th. And now since we have the same big base, right, we would get rid of those and we end up with 3n equals 4. Divide both sides by 3, so n equals 4/3. Here we've already got the same big base. We can go ahead and x those out. We end up with negative n equals 3n. We'll add n to both sides. So we're left with 0 equals 4n. Divide both sides by 4. And that tells me n equals 0. Number 15, I know 81 is 9 squared. And that means that I don't have to change the other side because I've got big 9s now on both sides, which leaves me with negative 3k equals 2. I don't have to move the 3k, I just have to get rid of that negative 3, so divide both sides by negative 3. K equals negative 2/3. So don't forget about that negative. 16, I can't get 27 or 81. I can't get 27 into 81, but I believe if we play around with this a little bit, we end up with 3 to the 4th. That's 81. And then 3 to the 3rd is the same thing as 27. And remember, your power to power rules, when we now have the same base, we get rid of those. Multiply these remaining pieces. So this is negative 8m equals negative 9m. Here I'm going to add 9m to both sides. So that leaves me with a positive 1m over here and 0 on the other side. So there's your answer. All right, so we're going to sketch the graph of each of these functions. Now, you've got on yours, and let me go ahead and write it in here, some other information that we need. All right, so the first thing we want to do is fill in that table down below. Just plug in those 5 values. I'll put those backwards here. Give me just a second. Let me switch those two up. So that's, we're going to plug in negative 2, negative 1, 0, 1, and 2. And this is just go to the calculator. My function, I should go back and look, 3 times 2 to the x. All right, so we're going to go 3 times 2. The first one is negative 2. So I'll hit enter. Oh, somehow I made an error. Hold. All right, well, there it is. I'm not quite sure, maybe because I didn't include my parentheses. So when I plugged in negative 2, I end up with 0.75. So 0.75. And then we just continue that process. So now I do 3 times 2 to the negative first. Let me close my parentheses. And that'll be 1.5. So there's 1.5. And then just keep working your way through there. So take a moment and do that very quickly. Just plug and chug. And what we'll end up with is what you see right here. So we have negative 2.75. So we'll put it about right there. Negative 1, 1.5. 0, 3, 1, 6, 2, 12. And what we can see, we connect this thing. It looks like it's going to go down. It can get really close to the x-axis, but not quite cross it. So that actually tells us the y-asymptote is y equals 0. I can see the y-intercept right there is 0, 3. And then this is going up, so this is a growth function, right? Another way to look at this, remember, just looking at the function, there's your y-intercept. And then this is, that 2 is greater than 1, so this is exponential growth. So just looking at this one right away, we don't have any kind of transformations with number 18, so you should be able to tell right away, well, there's the y-intercept at 5. So I know that y-intercept here is 0, 5. And then this is less than, it's between 0 and 1, right? 1/2 is between 0 and 1, which tells me this is exponential decay. So I can go ahead and fill that stuff in right away. Now, just a matter of plugging and chugging. So take a moment, plug all those values, do negative 2, negative 1, 0, 1, and 2, just to start to get a feel for what this graph looks like. So those are the values. So take a moment, go put those back up here on your graph. So negative 2, 20, negative 1, 10, 0, 5. There's the y-intercept, right? There's the y-intercept. Perfect. That's exactly what we said it was. 1, 2.5, and then 2, 1.25. And so this thing looks like it's coming down here. Again, it's, if we look at a different function, or if we look at a different medium, if we go look at like Desmos, we'll see that that's going to get really close to the y-axis again, or x-axis, which is the line y equals 0, and it won't cross over. All right, so the last couple problems here. The new car costing $20,000, the value of the car depreciates at a rate of 12% a year. So what's the initial amount A? Well, that's $20,000. So the decay factor, right? This is depreciating. So remember, a decay factor means we have to do 1 minus R. Here the R, right? Since it's 12%, that's 0.12. So for us, our decay factor is going to be 1 minus 0.12, which is 0.88. So there's our depreciation value. So the function that models this, remember we want y equals AB to the x. So A was the initial amount, so y equals 20,000. B is the growth factor. And don't forget to raise it to the x power. So what's the price of the car after 15 years? So that's just a matter. Let's plug it in. So 20,000 times 0.88 raised to the fifth power. So take your calculator. Just be careful that you type everything in. You have enough zeros. And so what that will give us, $10,000, 554, and then we'll call it 64 cents. So the car is worth $10,554 and 64 cents after 15 years. Approximately how many years until the car is worth 6,000? This is where Desmos is going to be really, really helpful for us. So if we open up Desmos and we type in y equals 20,000 times 0.88 raised to the x power, as is, we don't see it, so we're going to have to zoom way out, keep zooming, keep zooming, keep zooming. All right, now we're starting to see it. All right. And the question that we're being asked, how long is until it's worth 6,000? So that's where, put a point on here. So you can see the value of the car are the y's. And so we're going to have to keep going out, keep going out, keep going out. Until we see, all right, now we got 6,000 happening. But maybe a little bit, the graph is getting a little too crazy for us. So let's play with the window a little bit. So I just kind of paused the video for a moment and played around with it. Now it's going to be a lot easier for us to work with. So there it is. After 5.5 years, looks like the car's worth $9,900. So keep going until we get down to $6,000. Oh, I went right past it. So it looks like somewhere in here between 9.4 and 9.5, it passes that $6,000 threshold. So maybe we'll say after 9.5 years. So approximately how many years after is it worth? So that looked like it was about 9.5 years. All right. And we'll do one more. A sample of bacteria reproduces at a rate of 70%. So this is growth, right? It's getting bigger. That's growth. So remember, growth is going to be 1 plus R. Here, our R equals 0.70. So our growth factor, 1 plus 0.70 equals 1.70. So there's that. The initial amount, a scientist initially has 15 bacteria, so there's A. So 15 there. So the function here is going to be y equals 15 times 1 point, excuse me, I put the point in there too soon. 1.70 raised to the x power. So how many bacteria are there after 3 days? So 15 times 1.70 raised to the third, and that to me is just, you know, plug that into the calculator is as simple as anything else. So 73.7, so we could say 73 or 74. Either one of those would be fine. And then how many days until there are 650 bacteria? This is where, again, we're going to go to Desmos for this one. So let's clear out what I had before. Now I have 15 times 1.7 raised to the x. And here, I can zoom in a lot more on this one. Just to get a better feel for what I'm looking at. And the question again, right? How many days until there's 650 bacteria? So go along the edge here until we get up to 650. So there's 584 bacteria in about 7 days. Okay, so there you go. There's a better look at 7. After 7 days, there's 616 bacteria. But again, we want to know 650. So keep going until we get to 650. There's 649. So somewhere just over 7 days. So we'll call it about 7 days, right? So at 7.1 days, there's 649 bacteria. So let's call it just over 7 days, or we could just say about 7 days, according to the graph.